In our last video, we started to talk about direct proof, and we used that to try and prove some statements about even and odd integers. So in this video, we're going to generalize this to the idea of division. So for integers a and b, we would say that a divides b, and we write that with this notation here, a vertical line b, if there's some integer c such that a times c equals b. So this seems a little bit wordy, but all this is really saying is that if a divides b, that just means that b, the second number, is a multiple of a. Or, alternately, that a is a factor of b. And we would write a does not divide b if a does not divide b, right? If the vertical line with the slash through it means a does not divide b, so b is not a multiple of a. Just to get a sense of what this means here, you could say, for instance, that 3 divides 12, because 12 is a multiple of 3. Similarly, 3 divides 18, 3 divides 60. All of these things are true because these numbers on the right, 12, 18, and 60, are all multiples of 3. Right? We could write 12 as 3 times 4, 18 as 3 times 6, and 60 as 3 times 20. So you can express all of these as 3 times an integer, so 3 divides all of these. You could even say 3 divides 0 because you can express 0 as 3 times 0. Actually, any integer will divide 0. So, as a non-example, you couldn't say that 5 divides 12. This is not true. 5 does not divide 12, and that's because 12 is not a multiple of 5. 12 is not equal to 5 times c for any integer c. Okay, so this is just all this notation means. One thing to be careful of, this symbol, this vertical bar, it's a statement. We're saying a divides b, or b is a multiple of a. It's not a division line. We're not dividing a divided by b or anything like that. So it's a common mistake that I see people write it as like a fraction. It's not a fraction, it's a statement. Right? Think about it like the way you would use an equal sign or an inequality sign, right? It's really a statement about two integers, how they relate to each other. Okay, now let's look at an example. Suppose a, b, and c are integers. We want to prove that if a divides b and a divides c, then a also divides b plus c. So to get a sense of whether this is correct, I'm going to just try some examples here. I'm going to choose some various possible values for a, b, and c so that they satisfy the hypothesis, and then check to see if those values of a, b, and c also satisfy the conclusion. So if a divides b and a divides c, let's say I let a be equal to 3, b be equal to 12, and c be equal to 18, then it's true that a divides b and a divides c, because 3 divides 12 and 3 divides 18. Is it also true then that a divides b plus c? Is it true that 3 divides 12 plus 18? Well, 12 plus 18 would be 30, and yes, 3 does divide 30 because you can express 30 as 3 times 10. In other words, 30 is a multiple of 3. Okay, so it worked for this example, but in order to really prove this statement, it needs to be true for all integers a, b, and c, that if a divides b and a divides c, then a will also divide b plus c. So to prove this, we need to come back to our definitions of what it means for divides. Right? Now I'm going to set up an outline for this proof before I actually prove it. The same way that I did with the even and odd proofs. So start off with writing down what it is we want to assume and what it is we want to prove. So we have to assume the hypothesis. So we're going to assume that a divides b and that a divides c. And then we're going to prove the conclusion that a divides b plus c. So using the definition of divides, a divides b means that b is a multiple of a. In other words, a times some integer gives you b. Now, in our definition on the last page, we said a times c equals b for some integer c, but we don't want to use c twice within this problem. We already have c in play in some way. So I'm just going to say that by definition, this would mean that a times k is equal to b for some integer k. I'm just swapping out the variable k for c here. And similarly, if a divides c, that means, let's say, a times j is equal to c for some integer j. All right, now we want to prove A divides B plus C. So by the definition of divides, we're trying to show B plus C is a multiple of A. In other words, we want to show that A times L is equal to B plus C for some integer L. This is what we'd like to show. All right, so this outline should give us a sense on how to get started on our proof. What we need to do is start off by writing our general assumptions for the proof. So let A, B, and C be integers, and then write down what our assumptions are. So we are assuming the hypothesis. In a direct proof, you assume the hypothesis and prove the conclusion. So we assume the hypothesis, which is A divides B, and B divides C. Now what does this mean? By definition of divides, this means that A times K is equal to B for some integer K, and A times J is equal to C for some integer J. Right? I just stole that right from my assume column. Now, we're trying to prove that A divides B plus C. In other words, try to prove that we can express B plus C as A times another integer. So it would make sense then that we'll use those two statements that we just wrote, these statements here and here, to try to prove that B plus C can be expressed as a multiple of A. So notice that we can express B plus C then as AK plus AJ, just substituting B with AK and substituting C with AJ. Now, this is almost what we're trying to prove, except we want to show that B plus C can be expressed as A times a single integer. So what we need to do is factor out that A, just like we did when we were working with even numbers and we factored out a 2. We can factor out an A, and now that inside the parentheses part, that K plus J, this really is the L that we were looking for up here. Right? We've expressed B plus C as A times some integer. How do we know that K plus J is an integer? Just like before, since K and J are both integers on their own, K plus J is an integer also. And so now we can say that by the definition of divides, since B plus C can be expressed as A times the integer K plus J, we have that A divides B plus C, which is exactly what we were trying to prove. Alright, so this is really the same basic steps that we did in the even and oddness proofs. It's just that we have sort of an extra definition in mind now, not just even and odd, but this generalization of divides. So let's try another example. This time, we still assume A, B, and C are integers, and we want to prove that if A divides B and B divides C, then A divides C. So again, we're going to try to think through an example to make sure this makes sense. Let's think of integers A, B, and C that satisfy the hypothesis, that satisfy A divides B and B divides C. So maybe something like 2 divides 6 and 6 divides 30. Okay, because 6 is a multiple of 2 and 30 is a multiple of 6. Is it also true that A divides C, that 2 divides 30? Well, sure. Okay, so it worked for this example, but how do we know it always works? Here we have to use the definitions again. Right, but what this is essentially saying is that if B is a multiple of A, and then C itself is a multiple of B, C should also in turn be a multiple of A. And that really makes sense intuitively. So before we do the proof, let's set up an outline with our assumptions and what we're trying to prove. Assume, prove. We assume the hypothesis, that's the if part, and then we want to prove the conclusion. So we're going to assume that A divides B and that B divides C. Alright, so for A to divide B, that means that A times K is equal to B for some integer K. And for b to divide c means that b times j is equal to c for some integer j. Now we want to prove that a divides c, so we need to show that a times L is equal to c for some integer L. Oops, for some L in z. Some integer L. Alright, this is going to give us an outline for our proof. Now let's go ahead and try to prove it. We start with our assumption, so let a, b, and c be integers. A, b, and c are in the set of integers, and assume the hypothesis. Right, in a direct proof, you assume the hypothesis and prove the conclusion. So assume a divides b, and b divides c. Alright, now using what we have in our assume column, which is just the definition of divides, by the definition of divides, this means a times k is equal to b for some integer k, and b times j is equal to c for some integer j. Alright, now, it's probably a good idea, I forgot to do this in the last one, but it's a good idea to let the reader know what it is you're trying to show. So we must show that a divides c, right? This is what we're trying to prove. Alright, so we're trying to show that c is a multiple of a. So we're trying to show something about c, right? So I'm going to start here. I want to show that c can be expressed as a times L. Now this is a little bit weird because in the past we had two terms that we could sort of manipulate, x plus y or x minus y or a plus b or something like this. This time we're trying to show something just about c. So for now, all we can really say is what we have before, which is that c can be expressed as b times j, which isn't really enough because we're really trying to express c as a times another integer. Okay? But we also know from this other statement here that b can be expressed as ak. So I can rewrite this one more time, substituting out that b with ak. And now by the associative property of multiplication, I can rewrite this as a times kj. Right, now this is starting to look like what it is we're trying to prove. We're trying to show that c can be expressed as a times an integer. We've expressed c as a times kj. So this kj here, this is sort of the L that we were looking for up above. How do we know that kj is an integer? Well, just like before, k and j are integers. When you multiply two integers together, you get an integer. So since k and j are integers, their product, k times j, is an integer also. Alright, and so now by definition of divides, since we've expressed our c as a times an integer kj, we have that a must divide c, which is exactly what we're trying to show. Alright, great. One last example. Alright, example 3. Suppose for integers a, b, and c, that if a divides c and b divides c, isn't necessarily true that a times b divides c. This is different because they haven't told you it's true. They haven't told you to prove it. They want you to figure out if it's true. So, again, it's probably helpful to come up with some examples to try to get a sense of what this statement is saying. So we want to find some examples of integers a, b, and c that satisfy the hypothesis, and then check to see if this conclusion would also be true. Alright, so we want a, b, and c so that c is a multiple of both a and b. Alright, so let's say something like, let's let c be equal to 24, and maybe we'll let a be equal to 3, and b be equal to 2, something like that. Right, because this would satisfy that a divides c and b divides c, because 3 does divide 24, and 2 also divides 24. Now, is the conclusion also true? Does a times b divide c? Well, a times b would be 6, and 6 does divide 24. Okay, so it worked in this case, which might lead you to believe that this is true. But we want to be careful. We don't really know for sure that it's true. And if we try to set up a proof, we'd actually run into some problems. The reason being that I kind of picked some convenient examples here that happen to work. If I had picked other examples, it wouldn't necessarily work. So using the same c equals 24, this time what if I let a be equal to 12 and c be equal to 6? Oh, sorry. C is already equal to 24. Right? This certainly satisfies the hypothesis. It satisfies that A divides C and B divides C because 12 does divide 24 and 6 does divide 24. However, does AB divide C? Well, A times B would be 12 times 6. That's what, 72. Does 72 divide 24? No, definitely not, right? 24 is not a multiple of 72. It's smaller than 72. It's not going to work, all right? And so we found an example of A, B, and C that satisfy the hypothesis, that make the hypothesis true, and the conclusion false. We found another set of examples that make both of them true. So what does this mean? Is this statement true or is it false? Well, if a statement is a universal statement, which this last example is a universal statement because we're trying to show that it's true for all integers a, b, and c, then all we need is one counterexample to show that the entire statement is false. So remember, a counterexample is an example of the variables which would make the hypothesis true, but the conclusion is false. That's exactly what we had in green on this last page. We had a, b, and c that made the hypothesis true, but the conclusion false. And so because we found a counterexample, even just one counterexample, that entire statement was false.